This video is to show you two free response questions that show up regularly on the AP Calculus exam. The first one we're going to talk about is tabular data. So where they've given you a table. This has showed up 10 times in the last 10 years. And we're going to go through some common questions or some common themes that we see in these problems. They might ask you to calculate an LRAM, left RAM, or an RRAM, a right RAM, or a trap RAM, with either equal or unequal intervals. So if you remember back to the practice A, we had an MRAM, and practice B had an RRAM. We could also see a question about an MRAM with in this case, the intervals will be equal and the midpoint will be given right in the table. And then typically, after they have you do that accumulation calculation, they have you explain the units and context of the problem. So an example would be having data in feet and then maybe we have a velocity in feet per minute. And so since an accumulation is multiplying length times width, we would end up with units of feet, and then you'd have to explain what the units of feet mean in context of the problem. Maybe that would be like the distance traveled or something like that. The other thing we can do with a table focuses on slope. So we can calculate, they might ask you for an average rate. Remember, rate is another word for derivative. So, and derivative is another, if we don't have a function, we have to do an algebra slope. So the average rate would be just calculating the slope using 2 points in the table. They could ask you for an average value question. Remember, average value is the integral divided by the width of the interval. So we could use the answer we got for one of the approximations above for accumulation and divide it by the interval width. And then if they give you a function, they could have you integrate it for the accumulation. And that's typically on the calculator if there is a calculator question. If the tabular question ends up being a calculator question, that's typically what they do is they have you just do an FND. So we're going to take a look at this question here. It has to do with temperature of water in a bathtub and over time. And oh, I take it back. It's just a regular tub, not a bathtub. But we have water in a tub and the water is being heated. So we can see from the table that for 20 minutes this water, the water temperature increases from 55 to 71. And then if we just kind of scan these, so it looks like we have a derivative here. We have just the the function here, w, so it looks like we have a derivative here. Looks like we're integrating the derivative. Looks like an average value here. And then we have a function that models the table. So when we look at part A here, it says use the data in the table to estimate the derivative of w. So when we talk about derivative, we're looking at the derivative at 12. If we notice 12 is between two data points, it's between 9 and 15. So the derivative, I'm just going to write it in Leibniz notation. If I say derivative, you think slope since we don't have a function. So I'm going to grab those 2 points on either side of 12. And plug in the values from the table, 67.9 minus 61.8, 15 minus 9, and I end up with a slope value of 1.017. So that's a good estimate of the actual derivative. And then if you notice, I rounded to 3 decimal places. Now we're going to have to interpret the meaning of your answer. This is the units portion. So if we look at what we calculated, these numbers refer to Fahrenheit. These numbers refer to minutes. So we're looking at the fact that the water, we have a positive derivative, so that means the temperature is increasing. So something referring to the water is getting warmer. by 1.017 Fahrenheit per minute. There's the units, and that's occurring at 12 minutes. So it's an instantaneous rate that we're estimating. For part B, we can use the data in the table to evaluate this expression. So we have to kind of pick apart this expression here. If we look at this expression, we're talking about the derivative, because we see the prime notation there, the derivative of an integral. So we're going to use the plot rule here. So I'm going to rewrite this in a way that you're used to seeing it. So we have the derivative of an integral, and we don't have an x here. If we had an x here, it would just be w of x. But we can still plop in these values. So we're really looking at w20 minus w0. So the water temperature at 20 seconds is 71. The water temperature at the beginning is 55. So we have a 16-degree differential between the beginning and the end. And so now to interpret that, again, we're going to keep it short. This is a positive value, so it represents an increase in water temperature. So we have to say something about the temperature increasing. So we could either just say that, or we could say the water is warmed by 16 degrees Fahrenheit in 20 minutes. So notice we've incorporated the units here in our answer to give those units, to give those numbers context with reference to the problem. For part C, it's looking for the average temperature of the water. So we recognize we have an integral here of a function, and then we've divided it. If we notice the bounds here between 0 and 20, so we know the interval width is 20. We've divided it by 20. So that's a definition of average value. So this is the function in the table, so this is the average value of the water temperature. And it's telling us we're going to use 4 subintervals. We're going to use a left Riemann sum. So remember, left Riemann sum means the left side of the rectangle is the height of the rectangle. And so if it's the left side, then we're starting with the first point, because that's our left side of our rectangle is right up against the axis, or the starting point. So we're going to start with this point. We're going to use this, 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 and this point. So we use the first through the 4th point, or the second to last point. 4 subintervals. Notice our interval width is different, so we're going to have a different rectangle width each time. And then we're going to, again, we have to answer a question in context of the problem. So let's start with setting up the left Riemann sum, or the LRAM. So we have the first interval width is 4 minus 0. And the first height is 55. And the second rectangle width is 9 take away 4, which is 5. And the second height is 57.1. The next rectangle height is 15 minus 9, that's 6. And that height is 61.8. And the last rectangle width is 20 minus 15, which is 5. And the last rectangle height is 67.9. So there's the LRAM. And then I'm going to go ahead and divide it by 20 right away. Remember, this is a calculator question, so you can just plug all of this into your calculator. And you end up with an answer of 60.790. Notice I'm rounding to 3 decimal places. So now we have to explain whether this is an over-under estimate. And so we have to kind of reread this problem statement to see if we can get an idea of what the function is like. So we see this term here, strictly increasing function. Twice differentiable just means it's differentiable, so it's smooth throughout this 20-minute interval. And so if it's strictly increasing and smooth, then we know that these rectangles are going to be underneath the function, since we're lining up the left edges. And that being the case, if the rectangles are underneath the function, then it would be an underestimate. For part D, it's asking us to extend what we know away from the table. So we're looking at the time interval from 20 to 25 minutes. So out here where we don't have data. We're given a model. The model looks like this, and the model is of the derivative, which means if we want information about the water temperature, we have an accumulation problem out here that we have to work on. Notice the derivative is pretty nasty looking. They don't expect you to integrate that by hand. I've seen from time to time no calculator questions that ask you to integrate, but the functions will be much simpler. So this is definitely a do in your calculator sort of problem. We have a rate. We have to integrate to get accumulated temperature because our table is in terms of temperature, not in terms of rate. So we're going to accumulate. So we want the water temperature after 25 minutes. And so we need to know how much the temperature has changed in that 25-minute period. And then we're going to subtract off the temperature, what the temperature was at 20 minutes. So we'll subtract off that 71 degrees. This should be a minus sign, by the way. So the easiest way to do that, because we're going to use an F-int here, is we're going to want to put that as y1 in our calculator. And then I did this a little differently on my calculator here. What I did is I went from 20 to 25. So that's just the accumulated temperature from 20 to 25 here. And then I added the 71 here to get the final answer. You can accomplish that both ways. So this should be a 20 here. This is a typo. And so this, when you have put the equation into F-int here, that makes it easier if you already have the equation in y1 so that you can use your vars key. So we're going to go from 20 to 25 of that function, get that accumulated temperature and add it to 71. So our water temperature is 73.043. Notice I've rounded to 3 decimal places, degrees Fahrenheit, after that 25-minute period. The next question is a slope field question. That's a very common question type. It's shown up 7 times in the last 10 years, all in the no calculator. So you're not going to see this anywhere other than no calculator. So the calculations will be pretty straightforward. Typically, they ask you to graph a few points of the slope field. I would suggest making a table of those values before trying to draw them. Look for the dots on the graph. Don't graph more than you have to. Sometimes they might give you the slope field and ask you to sketch a particular solution through a specific point. A lot of times they're going to ask you to separate and solve the differential equation with an initial condition. That's really common. I would expect to see that. Since we're talking about a differential equation, that's an equation for a slope. And so we can then, since we can find the value of a slope at a specific point, we can ask you to write an equation for a tangent line at that point. So, you know, we'll show you how to do that. That's pretty simple. And then we might ask you to use the equation for that tangent line to approximate a y value in close proximity to that point. Again, that's not too bad either. So the only real calculus is solving that differential equation. So if we take a look at a specific question here, we have a differential equation, looks like that. And we have an initial condition, when x equals 0, y equals 1. So it looks like we're going to have you work with a slope field, write an equation to a tangent line, and use it to approximate, and then do an integration to find a particular solution. So in part A here, here's the portion of the slope field that they actually give you. So they don't really actually have you make the slope field. What we're going to talk about here, I've highlighted a few locations in red just to kind of get a big idea of what this slope field looks like. Let's practice kind of highlighting a few problems like we were doing in the unit on slope fields. For instance, let's look for values that make the derivative or in other words, the slope equal to 0. So if we look at this, when we put 3 in for y, we get 3 minus 3, which is 0. 0 times anything is 0. So when y equals 3, we have 0 slope. So we should be able to come up to y equals 3 on the graph and draw horizontal slope lines across the graph. Another value is cosine of x is 0 at pi over 2 and minus pi over 2. That's the top and the bottom of the unit circle. Right, so if we think about our unit circle here, cosine is the x-coordinate, so the top and the bottom are where the x-coordinate's 0. So that x-coordinate of negative pi over 2 is roughly 1.5, so notice I have horizontal slope lines here, kind of about where these slope lines are symmetrical, right in the middle there. So we know we have like a max over here and a min over on this side. So as far as sketching a particular solution here, first of all, we're gonna graph this initial condition when x is 0, y is 1. So that's right there. And then what we want to do is you want to follow the slope lines out from that point in both directions. So the slope line goes up and flattens out and then comes down. So we're going to draw that, and then as we go in the other direction, it's pointing down, flattens out, and then comes back up again. So it's going to look something like that. So notice I've followed those slope lines pretty, I've tried to stay pretty parallel to any slope line I was drawing over with my curve. So that's a sketch. As the height of this and the depth of this, or the valley here, they give you a little leeway, but it's definitely not symmetrical. We can see that the slopes over here are different than the slopes over here. For part B, it says write an equation for the line tangent to the solution at this point 0, 1. So this is an algebra question. We need a slope and a point. We already have the point, it's 0, 1. So all we need is the slope. So when I say slope, you think derivative. And so here is the derivative. Notice I just called it m because slope and derivative right now are being used as the same thing. So I'm going to go ahead and plug my 0, 1. So this is going to be 1, this is going to be 0. And then I'm going to go ahead and figure this out. And this is a no calculator question, so they're going to give you easy cosine values. Cosine of 0 is 1, right? 0 degrees is over here on the right side of the unit circle. So here's our unit circle, here's our right side. That x-coordinate is 1. So 1 times 2, so our slope is 2. So now we have a point, now we have our slope. We can go ahead and put that into the point-slope form of the equation. So we have y minus 1 equals 2x minus 0. Don't simplify it, you're done. That is the equation for that line. The next thing it says, we need to use the equation to approximate f of 0.2. In other words, function notation here. We want to approximate the value of the function f, that's the y value, when x is 0.2. So that being the case, we'll now have to kind of simplify this for y. So we'll go ahead and distribute the 2, bring the 1 to the other side. So really this line is 2x plus 1, has an intercept of 1 and a slope of 2. That's the tangent line. We'll draw that in just a second. So we know our x value is 0.2. So we're going to put in 0.2. Notice I changed the y to function notation. 2 times 0.2 is 0.4, plus 1 is 1.4. So the slope value is 1.4. So here's that tangent line going through 0, 1. It's got a slope of 2. Here is 0.2, and that is about 1.4. For part C, it says find the particular solution to the differential equation with that initial condition as x equals 0, y equals 1. This is kind of the meat and potatoes, so to speak, of question 6. It's probably worth 6 of the 9 points. So the more you can do here, the better. So let's start out with, we know that when we see the term particular solution, we have to separate the x's and y's, and we have to integrate. So let's start. so that, you know, that kind of gives you the idea of the x's need to be on one side, the y's need to be on the other. Let's start with writing the differential equation, and then we're going to perform algebraic tasks to separate. So here's the differential equation. So algebraically speaking, let's get rid of the fraction, so to speak. So we're going to multiply by dx. We're going to end up with this. Dx is now on the other side. Okay, so notice all my x's are on the right side. I can leave my x's alone. Now I can divide by the y term, and we're going to bring anything that's added and subtracted to the y with it. So we're going to divide by 3 minus y, and we're going to get this. So now my y's are on the left, my x's are on the right. So I've separated everything out. Now we're going to integrate this. So I'm going to put my integral sign on either side. Notice I changed the way this looks. Instead of dy divided by 3 minus y, I said 1 over 3 minus y dy. This hopefully helps you realize that we have a natural log here. So we're going to have a natural log of 3 minus y, and then we're going to have to divide by the derivative of this, which is negative 1. That's the u sub or the reverse chain rule, kind of all packaged into one step. And then I'm going to integrate this. Integral of cosine is sine, and then remember we always have a constant of integration. Very important to put this here. We always put the constant of integration on the x side. If you get this far, you're probably into it for 3 or 4 out of the 6 points. So if you can make it this far, you're in really good shape. I'm going to go ahead and bring the minus sign up front. And then I'm going to go ahead and put the minus sign on the other side. Now, notice I've stuck it with the minus sign. I kept the c a plus c, because if we had a minus c here, it would still be a constant. It would just be a negative constant, and that doesn't make any difference. So I'm just going to move this minus sign over it with the sign. And then I'm going to exponentiate both. So at this point, you probably do it for 5 of the 6 points. Maybe 4 or 5 of the 6 points. Because at this point, we're really just doing algebra and logarithmic tasks. So when I exponentiate both sides, it looks like this. The e raised to this is just 3 minus y. E raised to this looks like e raised to that power. And then now we got to incorporate the particular solution. So now what we're going to do is we're going to put in 0 and 1. So notice how I rewrote this, because e to the minus sine x plus c, remember e to the c, if we use our power rule here, e to the c is just a constant, so I'm going to bring it out to the front. And I'll put in my 0 and my 1. And so I get a constant equal to 2, because 3 minus 2 is 1, e to the 0 is 1, so c equals 2. Now I can put that back into here, and there is my particular solution. Now it is asking you to find y equals. So we really do have to solve this one for y. We can't leave it like this because it's asking for y equals. So I'm going to go ahead and take the y over here and take all that stuff over there. And we end up with 3 minus 2e to the minus sine x as our particular solution.